Hi, my name is Emiliano, and with my team, Javi, Cesar, Emilio, and I will be discussing arithmetic sequences in series. As the name implies, arithmetic sequences are sequences of numbers. What makes a sequence arithmetic is that there is a common difference between each term. This means that if you subtract any two consecutive terms, the difference will always be the same. This number is called the common difference, and by knowing the initial term and the common difference of any sequence, we can know every single number. An example of an arithmetic sequence is all numbers from 1 to 100, for example, or all integers from 1 to infinity. The common difference would be 1, since each term, for example 1, 2, 3, 4, 5, would be increasing by 1, and the initial term would be 1. Arithmetic series are sums or partial sums of arithmetic sequences. These partial sums can be found by formulas. In fact, the first formula for finding the sum of arithmetic sequences was found in 499 AD by an Indian mathematician astronomer, and the formula was said to be accidentally rediscovered by Carl Friedrich Gauss.
Oh, hello there. I'm Emilio, and this is what are arithmetic sequences and how can I use them? So, what are arithmetic sequences? Well, let's start first with a quick definition. Arithmetic sequences are a series of numbers that have a common difference between them. That means that they all follow a same rule, and you can know which number comes next. For example, take a look at this sequence. What if I asked you what is the 24th term of this sequence? Instead of counting plus 2 plus 2 plus 2 until you get to the 24th number, an easier way would be to use this formula, in which A equals the first term, which is 2, D is equal to the difference between each number. For example, here you find it by doing 4 minus 2. That is equal to 2. So you put it here. The difference between each term is equal to 2. And then you solve. For example, here you will do A of 24 is equal to 2 plus 2n minus 2. That would be equal to A of 24 equals 2n, and then you plug the n to the number that you're looking for, the term that you're looking for, which is 24. That is 48. And that's how you find the term you're looking for.
Oh, hi there. I'm Cesar, and I'm going to demonstrate the first formula of the arithmetic sequences. Now we're going to demonstrate this formula. First, we're going to write a simple series that will be A1 plus A2 plus A3. Then we know that this term is A1 plus D. That is the difference between each term. Then this is going to be A1 plus 2D. So 2 times the difference. So then we're going to make a new series calling A plus this term, that it will be A plus D plus A plus 2D plus it will be the formula we used previously, A plus D times n minus 1, and we know that n is the term we want to know. So now we're going to write another series and then we can just flip out this so we can sum these two series. So we're going to start from the end. It will be a plus d times n minus 1 plus a plus 2d plus a plus d plus a. Then we're going to sum these two series, and it will be 2Sn equals a plus this term, so it will be 2a plus d times n minus 1 plus these two terms, that it will be 2a plus d times n minus 1. Since there are the same terms, we can just leave it to 1, multiplying by n. We're going to have 2a plus d times n minus 1. And finally, we're just gonna take these two to this side so we can divide it by 2. Well, so we can have the formula from the beginning, n times a plus d, 2a plus d, sorry, times n minus 1 over 2.
So now we're going to demonstrate how this one is actually equal to this one. Let's begin. So we already know that S of n is equal to 1, a plus 1 plus a2 plus a3 all the way to a n minus 1 plus a n. But as my friend and my colleague over here already explained, we can write this as a1 plus d, a1 plus 2d, etc. until we get here, which is actually a1 plus d n minus 1. We can arrange that as follows: a plus a1 plus d plus a2 plus d, a1 plus 2d all the way to a1 plus d n minus 1. We can also add another one, the other sequence as Sn, starting from the end, writing it as an plus an minus d plus an minus 2d and so on. And here we would write an minus d n 1. And as you can probably tell, all of these cancel each other. D, 2d minus 2d, and so on. It would actually end up looking like this. 2Sn is equal to a1 plus an plus a1 plus an forever. Now we can simplify this by just turning all of these extras to n, since that's the term you're looking for, and it would be end up looking like a1 plus an equals to Sn. That looks kind of bad. To Sn. You can simplify this by just dividing by 2 and dividing by 2 over here, and that would leave us to n divided by 2 a1 plus an equals Sn, and that is equal to what we were talking about in the beginning, which is equal, to this one over here, which is equal to that one, because we use the same method, using different variables.
There are many possible applications for arithmetic sequences in series. This is such a broad term, such a wide a subject that can be applied to most fields of study, and even common issues every day. So one of the most obvious or widely used or talked about applications for arithmetic sequences and series is the Fibonacci series. This is a particular set of numbers that can be found in nature, for example, in the way that tree branches grow, or in sunflower petals, or in many other places. And also derived from this series is the golden ratio, which is said to be the most aesthetically pleasing proportion of all. So this can also be applied to design, for example. Arithmetic sequences and series can also be, for example, used to find the amount of seats needed to fit an amount of people, or many other topics.
So, I'm Xavier, and we're going to see a few problems with arithmetic sequences. So these are 3 different problems, and first, to see if we can work with them, we have to define if they are actually arithmetic sequences. To do that, we have to see which number we have to add from the first term to the second term, and then to the third, and so on. So we can see that in this first sequence, we have to add 3 to get to 4, as is the case to get to 7, and then to 10. So this one is in fact an arithmetic sequence. Then, for the second sequence, we'd have to add 3 minus the square root of 3 to get to 3 from the first term. And then to get to the third term, we just have to add the square root of 3. So it is not in fact an arithmetic sequence, and in turn it is a geometric sequence, so we're not going to work with this one. Then, for the last sequence, at first it is tricky, but then if we really focus on it, we can tell that to get from the first term to the second term, we have to subtract 2/3. And then we do the same to get from 5/6 to 1/6, and then the same to get to minus 1/2. How do we know that? Because 3/2 is the same as if we had 9/6, and then 2/3 is the same as having 4/6. So then with that we get 5/6, and then from 5/6 minus 4/6 we get 1/6. And then from that, if we subtract again 2/3, we get minus 1/2. So now that we know that, we're going to find the nth term of each sequence. So if we want to find the 11th term of the first sequence, we have to use this formula. To do that, we have to write the nth term equals the first term, which in this case is 1, plus the number that we're adding subsequently in each of the terms. In this case, it would be 3. So, plus 3 So if we want to find the 11th term of the first sequence, we have to use this formula. To do that, we have to write the nth term equals the first term, which in this case is 1, plus the number that we're adding subsequently in each of the terms. In this case, it would be 3. So, plus 3 times n minus 1. And since we're trying to find the 11th term, then we're going to put 11 minus 1. And this n would turn into 11 with it. So now we can see that 11 minus 1 equals 10, and 1 plus 3. 3 times 10 equals 30, and we get 1 plus 30, and then get 31. And with that, we can see that the 11th term in this sequence is 31. Now, if we want to find the 120th term of this second sequence, we're going to have to apply the same formula. So we're going to get that a of 120 equals 3/2, which is the first term, plus we have to add the number by which each term is being added. However, in this case, they're being subtracted by 2/3. So it's going to be a minus 2/3, and then n, which is 120, minus 1. So by this, we're going to get 119 times 2/3. And now we have to multiply that. So we're going to get 238 thirds. And then we're going to subtract that from 3/2. Now we have to find the common denominator. So it's going to be 6. And then 6 divided by 2 is 3 times 3 equals 9. Minus 6 divided by 3 equals 2. And then multiplied by 238 would be 576. Now we subtract that and we get 567 sixths. Oh, negative. Sorry about that. Now we're going to have to simplify that, and the way that we're going to do that is that we're going to turn it in halves. So we're going to divide that into 3. This is 126 is A, and then 27 is 9. So we're going to get minus 809 halves. And that is going to be our final answer of the 120th term of the second sequence. Thank you.